Hello everyone. Today we're going to start a new unit called Momentum. And the first lesson is an introduction into something called impulse and momentum. And I have here a picture of Isaac Newton. And the reason for that is when Newton wrote his 3 laws of motion, he actually wrote them from a momentum perspective. For example, he wrote his first law as when the net force acting on an object is 0, the momentum of the object does not change. Kind of like how we learned it, that an object's going to keep on doing whatever it was doing. The second law he wrote as the force acting on an object is equal to the rate of change of momentum of the object. We learned the second law is F equals ma. We're going to show in a few future slides how this is the same thing. And the third law he wrote quite simply as momentum is conserved. So he gave us a conservation law. So let's take a minute and review the conservation laws. So there are 4 conservation laws in physics. You might remember some of them. Conservation of mass. Mass cannot be created or destroyed. Conservation of energy. Energy is always conserved. And now we know there's a conservation of momentum. Momentum is always conserved. And there is a 4th, conservation of charge, that we'll learn later on this year. All right, let's do a quick self-check to make sure you really understand the conservation laws. Which of the following is not always conserved in a collision? So it really doesn't matter that it's a collision because conservation laws hold true for everything. So take a minute and think about your answer. If you chose kinetic energy, you're correct. Because conservation of energy really means conservation of total energy. But we know that energy can turn into different forms. And even though total energy is conserved, the specific type, kinetic energy, is not necessarily conserved. We're going to find out that this is going to become an important concept in the topic of momentum, so it was helpful to bring this up right here in the beginning. All right, let's look at momentum. What exactly is momentum? You might think of something and say, wow, that really has some momentum. But from a physics standpoint, momentum is a measure of an object's mass and motion. And momentum depends on both mass and velocity. In fact, momentum is equal to mass times velocity. So let's look at the variable for momentum. It kind of looks like a P. But it's really not a P. It's the Greek letter R, which is pronounced rho. So rho equals mass times velocity. Let's look at the units. Mass is in kilograms, velocity is in meters per second. So that means momentum, the units of momentum, are kilogram meters per second. So let's look at a couple of examples of something that would have momentum. So I have to have something that has mass and something that has velocity. So for example, I could have a bike or a car. I could have a bike with a small mass traveling 10 meters per second, or a car with a larger mass traveling 10 meters per second. And obviously the car then would have more momentum than the bike. But it's possible that I could have a bike that was going super, super fast, and I could have a car that was going really, really slow, and they could actually have the same momentum. So again, momentum depends on both mass and velocity. All right, Newton's second law, the way Newton wrote it, can also be related to F equals ma, which is how we learned it. Let's show how this can happen. So Newton wrote that the force acting on an object is equal to the rate of change of momentum of the object. So let's take those words and write them as a mathematical statement. So the force is equal to the rate of change of momentum. Rate of change means I have change happening per unit of time. And we now know that momentum is an mv. So I have mv final minus mv initial. By the way, when we have a delta, it's always final minus initial. Sometimes I forget that or mess that up. And one way to remember that is I alphabetize them. Final comes before initial. So the next thing I can do is factor out the m. And now I get the final velocity minus the initial velocity. But I'm going to pull that m out just a little bit farther, because now when I have the change in velocity on top over time, change in velocity over time is really the definition of acceleration. And so we find out that Newton wrote his second law this way in terms of momentum, but we learned it as F equals ma, and all we have done over the years is save ourselves 5 steps of work, and we have just jumped to F equals ma. But it's the same thing. All right, I also now want to take Newton's second law the way he wrote it and use it to derive what's called the impulse momentum theorem. So we're just going to do our derivation a little bit differently this time. So again, we have the force is equal to the rate of change of momentum, but this time let's multiply both sides of the equation by t. That would give us this. And now let's break down change of momentum. Well, change of momentum is equal to m times v, but if the momentum is changing, we know that the mass is not changing because that's a conservation law, so that implies that the velocity has to be changing. And if the velocity is changing, we can again expand that out to the final velocity minus the initial velocity. So really, the impulse momentum theorem is step 3 here. Ft equals m delta v. Let's write that over here. But the impulse momentum theorem really ties together two concepts that are obviously related. It ties together impulse and momentum. So Ft is impulse, but we're going to give a variable for impulse, and the variable we're going to use is j. And we already know that momentum is rho, is m times delta v. So we have two concepts that are equal to each other. Let's talk about what this really means. So if you have an impulse, which is really an event, such as a collision or an explosion, an impulse will cause a change in momentum. Or said another way, if you have a force that acts for a period of time, it will cause a change in velocity of the object. Now this is important. Force for a period of time. We've been talking about force for a long time, but we have never talked about how long the force is applied. So the concept of impulse is not only do you have a force, but we pay attention to how long that force is acting on the object. We'll go into more detail about that in a minute. Let's end here by looking at the units. So for impulse, force is in newtons and time is in seconds. And we already know the units for momentum. And it looks like they're different. But a newton is equal to a kilogram meter per second squared. And when you multiply that by the second, it ends up reducing to kilogram meter per second. So even though the units look different, they're equivalent to each other. So let's spend a few more minutes making sure we really understand the concept of impulse. And to do that, we're going to make up a story. I'm going to make up a story. And the story is that you are in a car and you are going to crash into a tree. Now, when you crash into a tree, it could be a deadly collision. And so crashing into the tree, the crash is the impulse. It's the event that is happening. So an impulse is an event. And during that crash, we want to talk about the force that's acting on your body and the time that you are involved in this crash. So how big is the crash? I'm just going to make up some numbers that are totally unrealistic. But how big is this crash? How big is the impulse? It is 100 Newton seconds. 100 Newton seconds. So I have the force times the time, and J is going to be 100. But there's lots of different ways that you could crash into the tree. So if J is 100, I want to make the time longer because then the force would become less on your body. So let's just look at this table for a minute to show how time and force are related to each other. So there's lots of ways we could crash into the tree. 100 Newton seconds. What if I crashed into the tree really quick? The time was 1 second. Then the force acting on your body would be 100 newtons. But what if I crashed into the tree twice as long, like going crash into the tree? Then the force acting on you is half. And if I could keep increasing the time it takes me to crash into the tree, I can decrease the force that acts on the person. For example, when I crash into the tree, what if your car goes crumple, 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 and your car starts to squish up? The reason we make our cars crumple is because we're increasing the time of the crash, and then we're decreasing the force that acts on the person inside the car. So the concept of impulse is that if we have an event that takes place over a longer period of time, we can reduce the force. So let's look at a couple more examples in a little bit more detail. So the first one is airbags. We're going to look at just a couple seconds of this clip. So in this clip, we have a person who's going to hit the barrier. And as you can see, the person goes forward because they are a piece of inertia. But what if the airbag popped out? If the airbag popped out, then that person would go forward for a longer period of time, and that would decrease the force on the person. So that's one way that airbags can save lives. Let's look at another example. I'll call it the egg toss or the water balloon toss game. So if I toss an egg to somebody and they catch it really fast, the egg is going to crack. But if they catch it longer by cradling the egg, we can decrease the force on the egg. Cradle. There's the cradle. All right, watch this next person. Crash! Because she caught it very, very quickly. All right, the next one. Throw an egg into a sheet. This is a classic physics example. So you take a bed sheet, you hold it up vertically, and the goal is to throw an egg at the bed sheet trying to break the egg. So let's look at this one.
Hey, welcome to Science Touch. I'm Hutch. This is science. If you throw an egg into a wall made of bed sheet, it will not break. Go! Hey.
Just that little bit of give was enough to increase the time so that the egg did not break. And the last one is an egg drop challenge. As you know, that you could drop an egg and maybe get it to not break by wrapping it in something. that gives it some push, or to drop it on something that gives it some push. But what's the point of the push? The push is to increase the time. So in this video, we're going to drop the egg on the left on the hard tile, and we have just a teeny bit of bubble wrap on the right, enough to increase the time that decreased the force on the egg. Let's do a quick self-check to make sure you understand impulse. Suppose you need to jump from a second-story window. Which of the following could reduce your force of impact? Jumping upward before falling to increase your time in the air. Jumping onto a concrete sidewalk so you land very quickly. Diving downward with an initial velocity to decrease your time of fall. Jumping into a trampoline to increase your time of impact. Yep, the trampoline. The trampoline is just like the give that the sheet had that allowed the egg to experience a decreased force. All right, so now hopefully we have a better idea of what impulse is. So next, let's look at how you can calculate impulse from a graph. So it says impulse can also be determined from a force versus time graph. So if you knew the force that was acting on something and you knew the time, we can find the impulse. So in this example, we have a constant force. We have a force of 5 newtons that is going to act for 10 seconds. So the area under the curve of a force versus time graph tells us the impulse. So what is the area under the curve? It means that if you take that force and that time and you make a shape like this, like a rectangle, the area of this rectangle tells me the impulse. But let's look at this to make sure you understand why the area under the curve is the impulse. So the area under this curve, when I say curve, it's a straight line, but we call it the curve. It's a rectangle. So how do you find the area of a rectangle? Length times width. What's the length? What's the width? That would be 10 times 5, and that is the impulse. And so the units turn out to be Newton seconds, so that tells me that the area under the curve has to be the impulse. And since impulse is equal to momentum, the area under the curve also tells me the momentum of the object. So in this example, the force was constant. But in real life, the applied force normally varies. So in this situation, we have no force, and then we have an increasing force, then a decreasing force. And we can see in this example that the collision took place over 8 seconds, from 1 to 9. So there's my 8 seconds. And this time, what is the impulse? Well, the impulse is still the area under the curve, but this time the area makes a triangle. And the area of a triangle is 1/2 the base times the height. So if we calculate the area of the triangle, we'll know the impulse. So we have 1/2, the base is 8, and the height is 8 newtons. And so we get 32 Newton seconds. So the impulse of this collision is 32, and the momentum of this collision is also 32. All right, the next thing is that when you have a graph, impulse can be positive or negative. So impulse above the x-axis is positive. This force is happening in the positive x direction. And impulse below the x-axis is negative. So to find the net impulse, I'm still going to find the area of each shape. And so here I have a triangle. So 1/2, the base is 3, and the height is 6. So that's going to give me an impulse of positive 9. And then over here I have a rectangle, and so the base is, or the length is 2, and the width is 4. But it's negative because it's happening below the x-axis. So when I add them together, the net impulse is going to be positive 1 Newton seconds. All right, let's do a quick self-check. A cart crashed into a foam barrier. A graph of the applied force as a function of time is shown in the graph. Determine the impulse exerted by the cart on the barrier. So as the cart hit the barrier, it had a constant force, and then the force decreased as it squished into the barrier. So what do you think the impulse is? If you picked 8, you're correct. So we could find the area of the rectangle plus the area of the triangle, and then we would know the net impulse. And since the impulse is 8, we also know the change in momentum is also 8. All right, let's now look at a problem that would utilize the impulse momentum theorem. So a 5-kilogram cart has a velocity of 12 meters per second after it has been hit with a 100 Newton force for 0.5 seconds. What is the initial velocity of the cart? Well, I have a velocity here, final velocity, and now they want an initial velocity. So I also see force and I see time, so that should make me think of the impulse momentum theorem. But because I have an initial velocity and a final velocity, that's a clue that I should break down the velocities. And now I'm just going to plug in the numbers that were in the problem. And we can find out that the initial velocity is 2 meters per second. Letter B says, what impulse did the cart experience? Well, impulse is force times time. So force times time, 50 Newton seconds. Letter C, what is the momentum of the cart? Well, if the impulse is 50, I know that the momentum is 50 kilogram meters per second. Or you might have thought about it this way. Momentum is m times delta v. Expand the delta v to the final velocity minus the initial velocity. And we can actually use the momentum equation to get the same 50 kilogram meters per second that we might have realized from part B. All right, the last topic that we have to look at is rebounding. And this is not hard, but it is the part that confuses people when you are jumping to solving problems and haven't looked at the notes first. So, what is rebounding? It's when you hit something and then it bounces straight back. For example, maybe you're playing tennis against the wall. So the tennis ball goes forward, hits the wall, and bounces back. Or it could be baseball. The pitcher throws the ball, and then the batter hits it back. So something is rebounding. So here's our example. We have a tennis ball, a 0.33 kilogram tennis ball that's traveling 5 meters per second. It hits the wall, and it rebounds straight back with a velocity of 4 meters per second as shown. What is the change in momentum of the ball? So the change in momentum is going to be the mass, 0.33, times the change in velocity. So the question is, what is the change in velocity of the ball? I'll give you a hint. It's not 1. Many people will assume it's 1. So how do I find the change in velocity of the ball? So there's two ways to look at this. Method 1, you could talk to yourself and say, well, the ball goes from 5 and then it hits the wall. That's 5 to 0. That would be a change of 5. And then it goes from the wall up to 4. 0 to 4, that would be a change of 4. So I have a change of 5, a change of 4, add them together. The change in velocity is 9. And that is correct. Another way that you could find the change in velocity is to say change in velocity is the final velocity minus the initial velocity. So the final velocity, it's not 4. The final velocity is negative 4. Things that go in the positive x direction are positive. Things that point in the negative x direction are negative. So the final velocity is negative 4 minus the initial velocity, which is positive 5. Negative 4 minus 5 is a negative 9. So the change in velocity is negative 9. Up here I said that the change in velocity was positive 9. So that negative just tells us the direction. So when I find the change in momentum is the mass times 9, if you did it the top way, then you would get an answer of 6. If you did it the bottom way and got negative 9, you'd get an answer of negative 6. What does that negative mean? It just tells you that at the end of the story, the ball is traveling in the negative x direction. So that last negative sign in your answer isn't super important when someone says, what is the change in momentum? But it tells you the direction of the ball at the end of the story. All right, so this was an example of something that is rebounding straight into the wall and straight back. But what if you were playing tennis and you hit the ball at an angle? So rebounding at an angle is a little bit more complicated. So here we have a tennis ball that's traveling 10 meters per second, and it's going to hit the wall at an angle of 50 degrees with the normal, and bounces back with a velocity of 8 at an angle of 43 degrees with the normal. Calculate the change in momentum of the ball. All right, so first of all, what's a normal? A normal is a line that is perpendicular to the barrier. So these angles are measured with respect to this normal. So when I have my barrier, I always draw in the dotted line so that now I know what my angle measures are. All right, but the incoming velocity is not 10, because just like we did in the previous example, we need to have the velocity vector that goes straight in to the barrier and bounces straight back from the barrier. So basically I need the x component of this 10. So to get the x component of this 10, maybe I'll make a little triangle like this, and then I can talk to myself and use some trig. So since I know this 50, cosine of 50 would end up being the x component divided by the hypotenuse. And we can set my trig up over here and calculate that the x component of this incoming velocity is 6.43 meters per second. So now I know the incoming velocity. Now I need to know this outgoing velocity. Let's do the same thing. Let's make a triangle. And again, cosine of 43 will be the adjacent, that's the x component, over the hypotenuse. And we can calculate that the x component will turn out to be 5.85 meters per second. Now that I know the incoming and outgoing velocity, I can use method 1 or method 2 to find the change in velocity of the tennis ball. All right, so I need to find the change in momentum of the ball, and the change in momentum is going to be the mass times the change in velocity. And, so I have my mass. The final velocity is 5.85, but notice it's going in the negative x direction, so I put the negative in, minus the incoming velocity, which was positive, and I would end up with a negative answer, negative 4.05. And what does that negative tell me? That at the end of the story, my ball is going in the negative x direction. But when the question says calculate the change in momentum, 4.05 is also a meaningful answer. Okay, let's do a couple quick self-checks to make sure you really understand the concept of rebounding. So we have a 5-kilogram pellet that's traveling 20 meters per second. It hits a wall and rebounds with a velocity of 15. What is the change in momentum? Well, the change in momentum is going to be 5 times the change in velocity. So what's the change in velocity in this story? It's not 5. No, the change in velocity is 35. 20 to 0, 0 to 15, 35. In short, when something is rebounding, straight in, straight back, you end up having to add the velocities to get the change in velocity. All right, what if we have something happening at an angle? A ball traveling 10 meters per second strikes a barrier. What is the x component of the incoming velocity? What I'm trying to show you here is you need to pay attention to the angle measure. So when it says, what is the x component of the incoming velocity? I need the straight in velocity. So I could use the one up here, or I could use the one down here. Straight in. They're both the x component. Let's say I use the one at the bottom. Then when I make my triangle, I'm going to want to use 40 degrees, not the 50. And I could set up my trig where cosine of 40 would be the x component over the 10 and find out that the incoming velocity is 7.66. But what if you wanted to use the 50 degrees like the picture gave you? Well, then you just have to use a different triangle. And if you use a different triangle, it's not going to be cosine of 40 because the incoming velocity is opposite the 50. So then I would use sine of 50 is the x component over the hypotenuse, and I'll still get 7.66. So my point here is that you need to have the velocity that goes straight in and the velocity that goes straight back when something is happening at an angle. And depending on what angle is given in the problem, it could be a sine function or it could be a cosine function. Okay, let's look at the summary of what we learned today and some of our key takeaways. So we now have 3 equations that you can use to work on your homework. We have the impulse equation, Ft, we have the momentum, mv, and we have the impulse momentum theorem, which says those two things are equal to each other. We also know that impulse is an event in which a force acts for a period of time. The area under the curve of a force versus time graph will tell you the impulse, and it's also equal to the change in momentum. And when rebounding, you must take into account the change in both the incoming and outgoing velocities. And when rebounding at an angle, you need to use the velocity components that act perpendicular to the boundary. So I hope this was helpful, and you should now be well prepared to work on your first couple of homework assignments.